So you guys just learned, right? Velocity of a wave is determined by the frequency that that wave has, how many waves per second, okay? Multiplied by the wavelength, yeah? Okay, so you learned that. You learned that the velocity we can solve for if we know the wavelength and frequency, okay? But the velocity itself could change, right? If I gave you, told you to solve for frequency, you'd need to know what the wave's velocity was, and in principle, that could be any number, right? Well, in a minute here, what we're trying to do is learn how to solve for electromagnetic waves, light waves, okay? So light waves are a little bit different than all of the other waves that you've learned about, okay? Waves in the ocean can change speed. Yeah, you know, like a tsunami wave can move at hundreds of miles per hour, but typically waves only move, I don't know, a few miles per hour, right? They don't hit the shore at hundreds of miles per hour, certainly, right? Okay, so all waves are not created equally, okay? Matter waves, like waves in the ocean, they can change their velocity. Their speed can change, okay? And the speed is relative, yeah? If you run towards the ocean and a wave's coming at you, it would appear to you like the wave is sped up, but it's not. You know it's not because you're running faster, right? It's kind of like you knowing that a car passing you, if you're driving 60 miles an hour and a car is driving 60 miles an hour towards you, right? It looks like the car's passing you at 120 and you're standing still, right? But you know you're not. You know you're going 60 one way, 60 miles an hour the other way. You add those two velocities together, 120, right? Same reason why you know that cars traveling next to you are still moving, even though they don't appear to be moving relative to you, okay? So anyways, light doesn't work like that. Matter waves do not work like light waves do, okay? Light waves are different. So electromagnetic waves, including radio, TV, radar, microwaves like your microwave ovens, infrared light like the heat that you feel, visible light, what's letting all of us see all of us right now, ultraviolet, X-rays, gamma, cosmic rays, all of these waves, all of these things are waves, but they're not matter waves. They're electromagnetic waves, okay? They differ from water waves in that they always travel at the same speed, okay? So if a light wave is coming at you, if a flashlight is shined at you, and you start running towards the flashlight, you will measure, if you could measure, you will measure the light to be moving at 3 times 10 to the 8th meters per second. And if you run away from that source of light, you will also be measuring that light to be traveling at 3 times 10 to the 8th meters per second. Turns out, no matter how fast you run away from the light, it will always be traveling at 3 times 10 to the 8th meters per second, okay? That should sound weird to you, okay? For this reason, speed of light is given the designation of c. So let me try to show some of this relative velocity stuff. I need 2 people. One person who wants to sit in the chair and one person who's going to push the chair, okay? Who wants to sit in the chair? Who wants to push the chair? Come on up. I need 2 people.
I'll sit in the chair.
All right. Enrique's going to sit in the chair. Somebody needs to push the chair. Push it. Joe? All right, Joe's going to push the chair.
There's somebody weak.
All right, Enrique, you got that ball. You're just going to sit in the chair and kind of keep your feet off the ground. Right? And you can toss me the ball, right? So you toss me the ball, it travels towards me at some velocity, right? Get the ball. Then Joe, start pushing him towards me as fast as you can and throw me the ball. Okay, let's see. Does the ball travel faster when he's moving toward me? Yes, right? Why? He threw the ball at the same velocity. Why is it coming at me faster? Because he's moving relative to me, right? It's the same as if he was stationary and I came running at him while he threw the ball at me, right? If he throws the ball at 5 meters per second and is moving towards me at 5 meters per second, we get a total velocity of 10 meters per second, right? So now, Joe, you're going to pull him away from me and just throw me the ball. See how it almost doesn't make it to me, right? Let's try that again. Joe, do your best to pull him as fast as you can away from me and just throw the ball the exact same way you've been throwing it. Notice how the ball appears to move slower through the air, right? To Enrique, the ball is moving away from him, right? It's staying each time. You're throwing the ball harder now. You're trying to compensate, right? So he's throwing the ball harder. Try to throw it the same as you have been.
Okay.
Pull away from me. Ah!
I think if I am pulling it, my arm's going to move faster.
Okay, so that's relative velocity, right? Okay. So now instead of that, I give Enrique a flashlight, right? And button. So Enrique shines the flashlight at me instead of throwing the ball, right? And as he's stationary, go ahead and turn the light off. And as he's stationary, I would measure that light to be moving at 3 times 10 to the 8th meters per second. 300 million meters per second, okay? You turn the light on again. Joe, just push it towards me. Now you can't see it, right? But if I measure this light source moving towards me, well, guess what? I'm going to measure that light source to be moving at 3 times 10 to the 8th meters per second. I don't add on his velocity, okay? Something weird is happening with light. Light doesn't work the same as matter does. When a ball is thrown and Enrique's moving towards me, the ball is moving faster relative to how it was, right? But the light source is different. The light source will always measure 3 times 10 to the 8th meters per second, no matter how fast Enrique's moving away from me or toward me, okay? Even if Enrique is moving toward me at 99% the speed of light, I will still measure the light to be moving at 3 times 10 to the 8th meters per second. Okay, thank you. That's the end of that. This has weird. This has weird. You guys are great. Thank you. This has weird consequences. Okay, this has weird consequences for distance and time. Because remember, velocity is distance over time, right? And if light has a fixed velocity, no matter how fast he's moving, then either the distance between us or the time between us has to change, okay? This is the beginning of something called special relativity, okay? Special relativity is, as developed by Einstein in 1905, is this idea that light always travels the same velocity in a vacuum, no matter what, no matter your relative motion. That should seem weird because I just went over a bunch of stuff about how your relative motion to things being like thrown at you, right, matters, right? If Enrique throws me the ball at 10 meters per second, but he's being pulled away at 10 meters per second, the ball just falls to the ground, right? And if he's coming toward me at 10 meters per second and he throws the ball at 10 meters per second, we add those velocities and the ball is coming at me at 20 meters per second. That doesn't work with light. Light is always measured to be the same velocity no matter what. Now you just get to take that little idea and just pocket it, and we get to move on. Okay, but that's why. I mean, so you just read it. Okay, light just moves at one speed. Cool, but it has weird consequences. Okay, and that's what relativity is all about. Is that every observer measures the same velocity for light. Again, having the right measuring tools, but every observer measures the same velocity. So for that reason, the speed of light is given a designation, lowercase c, meaning constant. So we don't use a little v for velocity, we use a little c. Remember that velocity, frequency, and wavelength are the 3 things we need, right? You need to tell me velocity and frequency to determine wavelength. And you need to tell me wavelength and frequency to determine velocity, right? And so on, right? But with light, now you have a constant, okay? So for electromagnetic waves, your velocity never changes. This is a huge help, okay? Because now, remember, it's a formula with only 3 things, right? Velocity, frequency, and wavelength. Now your velocity is always known. It's a help, right? Your velocity is now always known. It's just 3 times 10 to the 8th meters per second. 300 million meters per second. Okay, so your new formula for electromagnetic waves, you put the C where the V used to be. Nothing else changes. So now how many things do I have to tell you for you to determine one of them? Well, you only need to tell me 1 now. Well, you in principle, I need to know 2, but I know that the velocity is constant now. I just know it, right? It's a number we know. We've measured it, yeah? So now you only need to tell me frequency or wavelength. If I know one of those, I can figure out the other. So I still have to know 2 things, but one of the things is a constant, doesn't change. And that's a huge, huge help for us. So let's look at an example. In fact, the first thing I'd like to do is remind you guys how to work with scientific notation. And actually, let's use the example, and that'll help us do it. So you don't actually have to do this as you go, but you don't have to do it, in silent. We're going to do it all together, okay? So here we go. Remember that light moves fast. So the velocities we were talking about, right, in this room were like 5 meters per second, 10. And that, by the way, is way faster than we were actually moving. Okay, we were moving like 1 meter per second or something. We were moving very, very slow in the room here. But the velocities we were talking about were relatively slow. Okay, the velocity of light, 300 million meters per second. Not 3 meters per second or anything close to that. 300 million meters per second. That's why when Enrique turns on the flashlight or I turn on the flashlight, it seems like as soon as I turn it on, that light hits the wall, right? It doesn't. It travels 300 million meters per second, so it gets to the wall very fast. But there's some time between when the light is emitted and when it strikes that wall and then bounces off the wall to my eyes, okay? Anyways, light travels fast. The wavelengths of light will be very, very short. Well, to be clear, they can range from miles long all the way to, nanometers or shorter. So the wavelengths of light get wild, but we deal with very big numbers and very, very small numbers. High frequencies when the wavelengths are small, and we always have high velocities. For that reason, scientific notation is the best and easiest way to express things in these equations, okay? We already have light 3 times 10 to the 8 meters per second. That's take the number 3 and multiply it by 10 to the power of 8. Okay. Said in another way, take the number 3.0 and start shifting the decimal point over 8 places to the right. Okay, and you get the answer of 300 million. Okay, anyways, if I wanted to solve for this, so the question is, a particular shade of green light has a wavelength of 5 times 10 to the negative 7 meters. So let's take 5.0 and shift the decimal point. Negative 7, so it's 5.0, right? It's take the decimal point and go 1, 2, 3, 4, 5, 6, 7. So that is the wavelength in meters, I'm double checking, in meters of visible light. It's a teeny number, right? But in scientific notation, it's easy to write down 5 times 10 to the negative 7, okay? So negative exponents make you very small numbers, positive exponents make you very big numbers. Okay, so reminders on how to work with scientific notation, and it's actually given here very well for us. We want to know what is the frequency in hertz, okay? Remember, we already know the velocity, okay? And frequency, you guys learned this already, frequency equals velocity divided by wavelength, yeah? So frequency equals C divided by wavelength. That's the formula that's being applied right here, okay? So frequency on the left-hand side is equal to velocity, which is C, 3 times 10 to the 8th meters per second, divided by wavelength, 5 times 10 to the negative 7. So now you go, all right, what do I do with scientific notation? You're asking me to divide with scientific notation, okay? You have to do this in 2 steps, 2 operations, 2 separate parallel operations. Just divide up, just split up that, okay? Do the numbers, do the integer numbers first on their own, and then take care of dividing the exponent stuff, okay, separately. So you're going to do 2 operations. 3 divided by 5 is our first operation. 10 to the 8th divided by 10 to the negative 7 is our second operation, okay? Now this first operation, is that hard? No, 3 divided by 5, 0.6, easy peasy, okay? This is also not hard, but you have to know what to do, okay? When you divide in scientific notation, subtract the exponents. So this is the trick. When you divide in scientific notation, subtract the exponents. So what this is really saying is 8 is the exponent, subtract -7. What do you do when you subtract a negative?
Two positives.
It makes positives, right? So you're really adding 7. Okay? To subtract a negative is to add a positive. It's like saying a double negative, right? So 8 plus 7 is really 15.
Yes, sir.
So that's your exponent, 15. So it's 10 to the 15. So you take 0.6, your first operation, 10 to the 15, your second exponent operation, and add them back together. Plug them back together. 0.6 times 10 to the 15. There's our answer.
Is it just because it's like the exponents that you can't say it's a -1? Because 8 minus -7 or will be a +1.
8 minus -7 is still going to be 50. So if it was 8 plus -7, right? So if this were a multiplication problem,
Yeah.
if we were saying 10 to the 8th times 10 to the -7th,
Yeah.
then you add the exponents. You go 8 plus 7, right? And then it would be +1, right? Yeah, +1. Right? Okay. But so the trick is, in scientific notation, when it's a division problem, you subtract the exponents from each other. In scientific notation, when it's a multiplication problem, you add the exponents together. That's the trick. 2 operations, first side, right side. So to the left of the multiplication, do that by itself. To the right of the multiplication sign, do that by itself. And when it's a division problem, subtract the exponents. If it's a multiplication problem, add the exponents together. Raise your hand if that's difficult or you don't understand what I said. Okay. If you don't raise your hand, I have no choice but to assume you understand this and to keep chugging forward. Okay? So if you have a question, super important to ask it. All right, so everyone should be okay with that, hopefully, as long as you understand the premises that I gave you. 0.6 times 10 to the 15, that is our frequency, okay? Now, to put it into scientific notation, you need to put the decimal point to the right of the first non-zero digit. What's the non-zero digit in this 0.6? 6. So shift the decimal point over one place to the right. It'd be 6. What would you have to do to your right side exponent?
Take off 1.
Other way. Right? You made your number bigger? Oh, no, you're right. Yeah, you're right. Take off 1, sorry. Take off 1. So you go 6.0 times 10 to the 14. Sorry, I was thinking backwards. 6.0 times 10 to the 14. So 0.6 times 10 to the 15, 6.0 times 10 to the 14 are the same thing. Okay? All right, excellent. And they also expressed it here, 600 times 10 to the 12th. That's fine too. Technically, in scientific notation, you're supposed to put the decimal point to the right of the first non-zero digit. So 6 would be the correct way to write this. Anyways, let's do another one. So, and also, by the way, notice in the question, they only gave you one thing. They gave you the wavelength. They did not give you the velocity, but you knew it already because light only has one velocity. Okay? Good. Let's do the next one. The frequency of red light is 460 trillion cycles per second. It's a big number, but we can fix it. They actually did fix it for us. Yay for them. So here we go. 4.6 times 10 to the 14 is 460 trillion in scientific notation. So wouldn't you rather work with 4.6 times 10 to the 14 rather than 460 with 12 zeros after it? Right? That'd be a big old number to have to write down all those 12 zeros, or 13 zeros actually, every time. when you're working with the formula. Plug it into your calculator, you got 13 zeros to enter each time, right? It's easier to do it in scientific notation. Just once you just accept it, you just go, all right, fine, it's easier, let's just do it that way. Anyways, there's our frequency, 4.6 times 10 to the 14 hertz. What's the wavelength? So then you go, wavelength is equal to velocity divided by frequency. 3 times 10 to the 8 divided by 4.6 times 10 to the 14. By now you know what to do with this. Looks difficult, actually isn't. Just split it in half, okay? Do the left side by itself and the right side by itself. So 3 divided by 4.6 is our first operation. No need to do it mental math. You just plug it into your calculator. 0.65. 10 to the 8 divided by 10 to the 14. By now you know what to do. Take 8 and subtract 14 from it. And you should get -6. So now you've got 10 to the -6 and 0.65. So you plug them together, 0.65 times 10 to the -6. And you have your answer. This is our wavelength in meters. It's a very small number, right? 650 nanometers, 650 billionths of 1 meter. That's the wavelength of red light, or at least this red light with a frequency of 4.6 times 10 to the 14. All right. So hopefully you're okay with that. It's just the wave formula, v equals velocity equals frequency times wavelength, but now our velocity is fixed, okay? So c equals frequency times wavelength. Great. You guys did great with that. That's the most mathy stuff you'll have to know. Moral of the story wise, I want you to understand that for light, that frequency and wavelength have an inverse relationship. Okay? An inverse relationship is when one number gets bigger, the other number must get smaller. Okay? Said in another way, if for electromagnetic waves, light, if the frequency of the wave doubles, the wavelength has to be cut in half. Okay? If one number gets bigger, the other number has to get smaller proportionally. Okay? Frequency goes up, wavelength must go down, smaller. Okay? Frequency goes down, wavelength must go up. Because the velocity is fixed. If the velocity were not fixed, then lots of things can change. But because velocity is c, that's the right direction for you guys, c, right? Those two things have a absolutely inverse relationship to each other. Okay, that's the story. Okay, that's what I want you to take away from this. Now let's talk about some in theory kind of stuff. Okay, this one is, what is the nature of electromagnetic waves? Like, we know they come from somewhere, right? Light comes from somewhere. We see light coming out of here, bouncing off of you guys, right? And getting to me, and bouncing off of me and getting to you. So what's the nature? What's it coming from? What did we learn about electrons and their orbital shells? We've learned some stuff. Last time we talked about the atom, right? One more time? Oh, good. So electrons have a magnetic field. What else do they have that you can't take away from them? What's their name imply? Because they're called an electron. On, by the way, at the end of the suffix means being, right? So it's a little electric being. Yeah, that's what electron means, okay? A little electric being. Then we know they're not like alive or whatever, right? But the point is that electron means a little electric thing, right? We know they're electric. That's what they have. They have electric charge. What did I tell you electrons do? Can't take it away from the electron. It has charge. It has negative charge, but that's not that important. But it has electric charge, right? It has mass, it weighs something, right? And it spins. It has spin, okay? You cannot take spin away from an electron. It just has it. It's like mass. You can't take the mass away from the electron. You also can't take its spin away. What happens when electric charges move, Sergio? You told me already. When electric charges move, what happens? Not power generates, but think about the spinning electron. Yeah, you told me already. What did you tell me? What I said, what do electrons have? Yeah, but before that. You said magnetism, right? Yeah, they have a magnetic field, right? When electric charges move, they generate a magnetic field, okay? Electrons are electrically charged, and they move, they spin, okay? On top of like moving through space, electrons spin. You can't take it away from them. They are spinning. They have something called angular momentum. That's spinning, okay? You can't take it away. It's a conserved quantity, kind of like energy, okay? They have mass, charge, and electric and spin, okay? These are things that the electrons never get taken away from them. Good. So, things like the push and pull of electric charges and the push and pull of magnets are so similar because they're the same thing. They are the electromagnetic force. So when you put a refrigerator magnet up against your fridge and it pushes or pulls away from the fridge, that's the electromagnetic force pushing or pulling away from or toward you. Any moving electric charge generates a magnetic field, along with its already existing electric field. The magnetic field is aligned to the north and south pole of the spin, right? So you can imagine like the ball is the electron and it spins, right? It's got some axis around which it's spinning, yeah? Like the Globetrotters spin a basketball on their hand, right? It has some axis up and down around which it's spinning. Again, like the Earth is spinning around an axis, right? As it spins, there's a magnetic field generated, kind of like my fingers are wrapping around from north to south pole. There's a magnetic field generated around the spinning object, okay? That magnetic field is perpendicular to the electric field. So the magnetic field goes top to bottom, and the electric field runs perpendicularly around like the equator of the electron, okay? And these are things that it has. Again, I cannot say this enough. You cannot take away spin from the electron. It is always spinning. So like a ball, right? I spin this ball, and when it lands back in my hand, it stops spinning, right? That doesn't happen for electrons. They're always spinning. It's a conserved quantity, okay? They have mass, charge, and spin. Can't take it away from them. So they'll say it again. Each electron, and by the way, I'm talking about electrons, right? But remember, there's also, in the nucleus of the atom, protons and neutrons. We're not going to worry so much about them. Almost everything we need to care about is going to be dealing with electrons and their spin, okay? So electrons always have an electric and magnetic field that can be manipulated. The electron can be moved. It can be oscillated, be pushed around, okay? Electrons do not have to be traveling down a wire in order to possess a magnetic field. They just have it, even when they're sitting still. It exists around them, okay? Now, if I put this, this is a foam ball. If I put it in like a tank of water and I wiggle the ball up and down in the water, right? What's it going to do to the water? Make waves in the water. And those waves are going to go away from to the edge of the tank, right? Away from the ball, yeah? That's an easy one. Kind of like dropping a rock in a pond, right? And you can sit there and shake the ball up and down all you want, and you're going to keep generating more and more waves, yeah? If I shake it once, if I shake it really fast, I'm going to generate waves with a short wavelength or that are moving very fast, right? If I shake it kind of slowly, I'm going to generate slower moving waves with longer wavelengths. So that's going to affect wavelength and frequency, how much I shake it, right? Okay, so electrons are kind of like that. Now, an electron does not it's not sitting in a tank of water. The thing that it's waving its electric field and its magnetic field. It just You move the electron up and down, you oscillate the electron, its electric and magnetic fields are going to start to wiggle, okay? Those wiggles move away from the electron at the speed of light because they are light. We detect the up and down disturbance in the middle of a swimming pool by the horizontal waves it creates. Again, ball in the water moving, right? Making wiggles in the water. The oscillations of an electron up and down create a wave disturbance in the magnetic field and the electric field surrounding the electron. And the trick with the electric and magnetic fields are that they're everywhere. Between you and me, between stars, between planets, right? They're everywhere, okay? It's just that, like, halfway from me to Joe, there's no value to the electromagnetic field. It's not doing anything over there, right? Until I wiggle some electrons and send that wiggles towards Joe or one of you guys, right? That's the deal. If all the lights are off in the room, right? We're not sending electromagnetic waves bouncing off from me to him, right? Or you guys to me, yeah? Anytime the electrons are being oscillated, they're wiggling the electric and magnetic field. Those wiggles, again, are the light, okay? That's why they're massless. They're just a wave in the electric and magnetic field. So strong electromagnetic fields around a radio station's antenna shake the electrons in the antenna, and those shaking electrons wiggle the electric and magnetic fields in a very specific way to create the right wavelength of electromagnetic wave, okay, to get to your car's antenna and wiggle your car's antenna's electrons and send that down the wire through your radio, and sound comes out of your speakers, okay? The wave causes the electrons in the car antenna to move up and down, including inducing electric current in your radio, and boom, you've heard something. So, radio waves, X-rays, all electromagnetic waves are waves, double waves, in the electric and magnetic field. There's a magnetic wave up and down one way, and there's an electric wave going the exact perpendicular direction to it. They're a double wave consisting of one electric wave and one magnetic wave, so we call them electromagnetic waves. They're transverse waves because they move in a direction, but the waving actually goes perpendicular to the direction of movement. Now what's neat is the electrons can wiggle just a little bit and make a very long wavelength. So, and keep this in mind. If the electron wiggles a little bit, so like, let me back step. If I wiggle the ball in the tank of water, I can make a slow moving wave. If I wiggle the ball very slowly, I can make a slow moving wave with long wavelength, right? If I wiggle the ball very fast, I can make a fast moving wave with short wavelength, right? For electrons, if they wiggle a little, they make the same velocity wave as if they wiggle a lot, okay? Because remember, the waves always travel at one speed, 3 times 10 to the 8th meters per second. So what can change? For electromagnetic waves, what two things can change? Think back to the wave formula. What are the two variables? Yeah, okay. So wavelength can change and affect frequency, or frequency can change and affect wavelength, okay? For an electron, if it wiggles a little bit, it makes a light wave with a long wavelength. If it wiggles a lot, it makes a light wave with a short wavelength, okay? It's the amount of oscillation that the electron undergoes that affects the wavelength, but super duper importantly, the velocity never is affected, okay? It's just the wavelength affecting back on frequency. Affecting frequency. Okay, so a little movement, long wavelength. A lot of movement, short wavelength, okay? We call all of these possible different wavelengths, we call them the electromagnetic spectrum. A spectrum is anything that can be measured in orderly, continuous progression. from big to small. Of the whole electromagnetic spectrum, from radio waves all the way to X-rays, what percentage of it do you think you can see? 100%? So do we see 100%? Can we? No. Because what stuff do we know we can't see? X-rays, infrared, right? Okay, so there's some stuff we can't see. So what would you guess? I don't actually know the actual percentage, but it's not 50%. It's not 25%. It's closer to like a single percent, okay? It's closer to single percent points. We can see wavelengths of light between 400 and 700 nanometers. That's it. If the wavelength is 350 nanometers, we can't see it. That's ultraviolet, okay? If the wavelength is 710 nanometers, we can't see it. That's infrared, okay? We cannot see things above 700 nanometers or below 400 nanometers. That's our visible light spectrum, okay? We can see a teensy percent of all of the possible wavelengths of light. Now, I've said this before in other classes. I teach other classes too, and I say this all the time. Other animals have different sensoria from us, okay? Other animals have, for one, completely different senses, right? Like bats have ultrasound or whatever. But other animals can see different wavelengths than we can see. We only see the 400 to 700 nanometer spectrum because we don't need to go harvest flowers to make food for our little insect babies, right? We need to use sunlight to see just general things in the world, right? And it turns out the sun produces the most light in the 400 to 700 nanometer spectrum. So it's not like a trick or some surprise that we see in that spectrum. That's just what the sun does best, okay? And we see what the sun does best because we grew up here on the earth, right? Being lit up by the sun. Okay, so we see what we see for a good reason. Okay, so the electromagnetic spectrum. It's a range of energies from unimaginably small wavelengths with incredibly high energies, all the way to wavelengths measured in kilometers or like miles long with extremely low energies. At differing energy levels, these radiations are distinguished by the different ways they react with molecules and particles. For example, you know that microwaves with wavelengths in the centimeters, okay, they can do things like heat up your food, right? Visible light lights up the room. Same type of thing, right? It's an electromagnetic wave. One of them's good at heating up your food. The other's good at producing light for you to see, okay? Infrared we feel as heat. Yeah, so all of these different things react differently with molecules. X-rays pass right through the body, right? And we can use them to make images. So all of these different electromagnetic waves do something, and they do something differently depending on the wavelength. There's this idea of resonance. So it's a wave, a wiggle, or a vibration, yeah, if you like. All structures, molecules, atoms, subatomic particles have a frequency, a vibrational frequency at which they are, in air quotes, tuned. Okay, we call that their natural frequency. Radiations at frequencies that match the natural frequency of an object will interact with it, being absorbed by it. Radiations at all other frequencies will penetrate right through it. For example, radio waves, when we send them out towards the sky, because our radio waves go everywhere, right, from our radio antennas and our radio stations, they will bounce off the ionosphere. It's part of one of our layers of the atmosphere. Okay, they will bounce off of it. Okay, radio waves go up, bounce off of the ionosphere, and bounce to a completely another part on the planet. They can wrap around the planet. Okay, so we can send radio waves over extremely long distances. Some of the first stuff they did with telephones, for example, right? Sending waves, radio over long distances too. Visible light, though, goes right through our atmosphere. You know visible light goes through your atmosphere. What data do you have that shows you visible light goes through the atmosphere? You go outside, and what data could you collect to tell me that visible light travels right through the atmosphere? Yeah, you can see the sun, right? Okay, so you know visible light goes through the atmosphere. Microwaves heat food that absorbs them, right? You know, like when you go stick your hot pocket in the microwave, yeah? What part of the hot pocket gets hottest?
Or you put around it.
You put a thing around, but it's the inside. The inside's like molten lava, and the outside stays kind of cold, right? Because the dry bread on the outside has less water in it, and microwaves are interacting with water, so it's like the sauce on the inside just absolutely bakes, right, and gets super duper hot, but the outside may not get as hot as quick, right? Drier bread, less water. Microwaves aren't interacting with the bread molecules; they're interacting with the water molecules and wiggling those water molecules. Okay, good. All right, so we're learning some stuff, okay? Let me just give you some of the electromagnetic spectra, and you can see kind of where they fall, okay? Let's start at the bottom. The longest wavelength stuff. Let me position this correctly. So at the very bottom, we have radio waves. Radar and TV, those are radio waves. You can also include the internet, like the Wi-Fi and all that stuff. Okay, that's in the radio spectrum. Energies are in the millionths to billionths of volts. So does it take much power to make radio waves? No. Now the reason why TV and radio stations have to have big old giant antennas, like on top of their, like the news people have those big antennas on top of their vans, right? You go to the radio station, then the big antennas way up high. It's because they have to send those waves over very long distances, so they make big amplitude waves. But to make that wave in general doesn't take much energy, okay? So it's easy to do. Wavelengths are in kilometers, fractions of a mile long, okay? Go up from radio waves, microwaves, higher energy. 10 thousandths to millionths of a volt. A volt is a unit of energy that we're going to get to be familiar with, okay? We use 50 to 120,000 volts in our x-ray rooms, right? So microwaves, thousands of volts. Wavelengths of centimeters or less. Infrared light, thousandths of a volt. Now we're getting more energetic now. Hundreds of microns. A micron is a millionth of a meter, millionth of an inch. Anyways, a micron's a tiny little unit of distance. Ultraviolet, hundreds of volts, tens of nanometers in length. So notice we're getting shorter. Our wavelengths are getting shorter, and our energies are getting higher. What's the relationship between energy and wavelength? Inverse, absolutely, yeah. Diagnostic X-rays are highlighted here. 30,000 to 150,000 volts. Wavelengths of a tenth to a half of an angstrom. An angstrom is 1/10 billionth of 1 meter. 10 to the negative 10 meters. So we're like a tenth of 1 angstrom. So they're tiny. Diagnostic X-rays are tiny in their length, and they require thousands of volts to create them. That's why our X-ray rooms have to use high energy transformers to produce enough energy to make X-rays, because to wiggle an electron hard enough to make an X-ray photon with short wavelengths, you got to put lots of energy into that electron. If you've been with me long enough, you learned that we fire electrons across a gap from cathode to anode inside of the X-ray tube at a high rate of speed and then slam it into a wall, right? That slamming into the wall is like wiggling the electron really hard, okay? And you're wiggling the electromagnetic field very hard and making very short wavelength photons. X-rays in principle can be up into the hundreds of thousands of volts and can have wavelengths down to smaller fractions of an angstrom than diagnostic X-rays do. So there is X-rays, like cosmic X-rays, the kind that come from outer space and that we create on Earth and whatever. But then there's diagnostic X-rays, the ones that are like useful for us, okay? Go up from that, gamma rays, hundreds of thousands, to millions of volts. Wavelengths in the billionths of a millimeter. And lastly, cosmic rays. Billions of volts in energy. Quadrillionths of a meter. So there is 1,000 trillion. That's a big number, right? But so a trillion is 1,000 billion. So it's 1,000,000 billion waves per millimeter. not meter, per millimeter, right? A million billion waves per millimeter. Okay, that's unimaginably small, right? Okay, so we can't picture it, right? That's the point. So these wavelengths get down to teeny lengths. Okay, here's the cool thing: of all of that spectrum, the entire visible light spectrum, red, orange, yellow, green, blue, violet, fits into energies between 2 and 3 volts. That's it. That's the whole visible light spectrum. Energies between 2 and 3 volts. Everything that you can see with your eyes lies between 2 and 3 volts of energy. Okay. And again, X-rays being in the hundreds of thousands of volts of energy. So it's the same thing as visible light. Our eyes just aren't sensitive to it. Electromagnetic waves can be used effectively. Okay, we can modify electromagnetic waves. Okay, so for example, you probably have heard of AM and FM radio waves. Okay, you're about to learn what they mean. AM radio waves are take a wave, a radio wave, and then modulate the amplitude. So the radio wave is the wave, and then you're going to add on top of it an audio signal that changes the height of the wave at different points. So you can carry an audio signal within a radio wave. Amplitude modulated waves are the signal comes to you at one frequency, but the amplitude of the wave changes. So it's got its own frequency. The amplitude changes have their own frequency. That frequency is the audio signal. FM, frequency modulated waves. So you have a carrier wave at one frequency. You have an audio signal that you strap onto it, and instead of the wave changing amplitude, it changes frequency at different points. That frequency change has its own frequency, and that is the frequency of the audio signal. So you can strap on an audio signal to a frequency modulated wave, or you can do it to an amplitude modulated wave, AM or FM, and you can send radio waves with signals in them. So this leads to the conclusion that your TV, at least the antenna type TVs, are essentially a radio receiver. Interestingly, the picture is carried by AM radio waves, and the sound is carried by FM radio waves. You have to use 2 separate waves, one for picture, one for sound. We have other things too. You guys have probably heard of radar, radio detection, and ranging. Remember, waves travel at a set speed, right? So you can send the waves out, and you can bounce them off of stuff and tell how long it takes for them to come back. You know how fast they travel, right? 300 million meters per second, so that's just a given, okay? And you can time how long it takes for the waves to come back to you. And you can determine if there are objects out in your distance, even if you can't see them, right? Because visible light might not travel through thick fog, or you're not going to use it at pitch black when the objects are 100 miles away, but you can send out radio waves through the pitch black and the fog, and you can bounce them back, and you can see that. So radio waves, by timing the return echo and multiplying by the speed of light, the distance to an object can be calculated. We know the speed. That's what's so cool about light, is it's always got a constant speed, and so we don't have to factor that in. It's just part of the deal. It's a constant for us. Microwave ovens use something called a resonator, a microwave amplification device that synchronizes microwaves to make them in phase with each other, and so all the waves sort of line up with each other, and that will cook your food. Kind of cool. We get to cook our food with microwaves. By the way, I think I've said this before, but you notice like your microwave oven has holes in the window, right? It's not just like a glass window. Those holes are smaller than the wave is. Okay, so the wave will, even if it comes straight out at you, will bounce right off of that mesh and bounce right back into the microwave. So you can see through it with visible light, but it's not clear to microwaves. Microwaves can't get out of it, so it's safe. That's why your microwave ovens turn off when you open the door, right? You can't like open the door with microwave oven on. You have a question?
How does it feel like a metal fork in there?
Yeah, so it's going to start to shoot electrons off of the fork. It's going to hit the fork and start firing electrons off of it, and you see that as like sparks and stuff happening. Yeah.
What about the everything grapes?
Yeah, I haven't seen what grapes do. What do grapes do? Oh, okay. Yeah, it's something, electrical arcing or something. Yeah, different things behave differently in the microwave. Like you can take marshmallows and stuff and make them like expand all crazy in a microwave. But yeah.